Good afternoon, ladies and gentlemen. My name's Daniel, and today I'm joined by my colleague Mark and Tim Bart from Hello, an AWS IoT company. And today we'll be looking at how to leverage Amazon Kinesis in building an IoT analytics platform on AWS. So what are you going to get out of the session today? Well, together we're going to explore two real use cases of an IoT analytics platform using the Amazon Kinesis family of services, and we'll see a demo of the IoT and Amazon Kinesis services in action, and then take a deep dive into a reference architecture of building an IoT analytics platform on AWS. And then we'll go and do a deep dive on the underlying architecture of the demo. And then we'll hear from Tim Bart, and he'll take you through Hello's specific use case on AWS and their journey and what they've been doing around their analytics and IoT platform on AWS. So by the end of the session, you'll have an appreciation of the AWS services required to build a serverless IoT analytics platform, and you'll be able to describe the functionality of Amazon Kinesis Streams, Firehose, and Analytics, and understand how to acquire, process, and store IoT sensor data. All right, so I'm going to hand it over to Mark, and he's going to take you through what you're about to see in the demo.
Thanks, Daniel. Good afternoon, ladies and gentlemen. So the example that you're going to see today is actually an example that we built for a boot camp here at re:Invent that we ran yesterday. And it consists of a number of environmental sensors. And you can see here we've got some rainfall sensors, temperature sensor, that little earth with the arrows is a vibration sensor, and a wind direction sensor. There's a weather station that collects all this data together, aggregates them, does a little bit of processing on an IoT device, and then forwards that data into the AWS platform for further processing. Out of the AWS platform, using a range of AWS services such as AWS API Gateway, Lambda, Cognito, we provide a global weather view. And one of the demos you're going to see today is the end-to-end user experience that's delivered by combining all of these services together. So the key services that we use to deliver the capability in the acquisition phase, the collection of data, is the AWS IoT service. Within the AWS IoT service, there's some capabilities, and we're using three key capabilities of the AWS IoT service in this acquisition phase. The first capability is the IoT rules. The second capability is the concept of an IoT thing, and the third capability is an IoT action. You'll also notice that we're using Amazon SNS within the acquisition phase of the architecture. Daniel will talk a little bit more throughout the presentation about how we use SNS as a fan-out mechanism for IoT data and how that can be beneficial in collecting and sharing that data across a range of AWS services. Within the processing component, we use some fantastic AWS services, Amazon Aurora and Amazon Redshift for databasing capability, Amazon S3 for object storage, again, Amazon SNS as part of the fan-out methodologies that we use, AWS Lambda, our zero administration serverless compute platform, and we make use of all three members of the Kinesis product family, Kinesis Streams, Kinesis Firehose, and Kinesis Analytics. As we head into the UI component that makes use of all the data that's being collected, as I mentioned, we use Amazon API Gateway. We make use of Amazon Elastic Cache. Again, AWS Lambda, which is seamlessly integrated with Amazon API Gateway. AWS S3, Cognito for authentication and authorization, and we make use of the JavaScript SDK. So when we show the demo to you, you'll have some idea about all the services that are being used to drive this demo. So when we lay out all these services end-to-end across this high-level concept that we're using today, you can see this is an absolutely broad set of architectures. One of the nice things about this design is that it's tightly aligned with the AWS concept of serverless. And what this means is we're able to use 10 AWS services and features, but within this architecture, there are 0 servers to manage. And what does this mean? It means a couple of things. First of all, there's no need to administer, manage, or scale any of that compute functionality yourself within the design. Secondly, there's no need to handle any of the scaling of these platforms yourself. So the ability for you to under-provision or over-provision is removed from your administrative overhead, and AWS will take care of ensuring that the appropriate resources are available to your application and your architecture on an as-need basis. And of course, this being serverless, the AWS pricing model comes into play, which is a utility, a utility pricing model, which means you'll only pay for what you use. So what I'd like to do is just take a few moments and share with you a demo of this architecture and what the users actually get to see as a combination of all of these services together. Whenever I see that video, I'm never sure whether to applaud the music, the content, or the technology. I think it's a fantastic demonstration of what can be done when we tie together these serverless architectures. And again, this was completely served and delivered in a serverless architecture. So there were not even web servers involved in delivering that content. Now, when we engage with our customers, we love to get feedback, but B, we love to be told what you need, and we love to deliver on these needs. And when we talk to customers about delivering architectures like the ones we've just discussed, we basically get 4 key asks that customers ask us to help them with. The first one is, can you help us ingest large volumes of real-time data from large fleets of distributed devices? And generally, these are going to be IoT devices. And to do that at scale. And when we talk about scale, we're talking about global scale. Not hundreds, not thousands, not tens of thousands, but millions of devices and trillions of messages. Customers ask us to help them perform advanced analytics on this streaming data and to be able to do this in real time so they don't need to manage that infrastructure and the complexity involved in doing that. They also ask us to help them process this data and to store the large volume of data to make it accessible for both real-time access but also historical access, so we can go back and look at statistics and trends over time. And finally, our customers ask us to deliver them solutions that eliminate capacity planning, scaling, and the management of any infrastructure. And the architectures that we've presented and the architectures that our colleague Tim will talk about are ones that represent these asks that our customers, have asked for. Why are you, our customers, asking for this? You're asking because designing for failure in global, real-time, distributed systems is really, really hard. It becomes extremely costly and requires significant infrastructure in order to achieve the level of scale and high availability that's required. Secondly, the infrastructure to build is extremely expensive, and that infrastructure that's required to process billions of devices, sending trillions of messages, is really expensive. What we mean there is only at global scale with a significantly large customer base with diverse requirements allow you to build out this infrastructure in a way that serves these needs. Thirdly, that management overhead in managing these sort of infrastructures and architectures that require high availability at global scale enforce a level of management overhead, and this scales. It puts scale limitation on organisations, but it also impedes organisational innovation and technology innovation within those organisations because they become quite focused on managing the technology rather than delivering services, capability and functionality to their customers. So AWS has taken on board the concept of doing all the undifferentiated heavy lifting for you, our customers. This means that you can focus on delivering those things that you're really good at, and especially delivering value to your customers. So what I'm going to do at the moment is I'm going to walk you through quite quickly a reference model. This reference model is the model that we use to build out the architectures for the boot camp. They're reference models that will be quite similar when you apply them, for example, to the architecture that Tim will talk through. Architecture, from an AWS perspective, starts with security. Security is what we call at job zero. It's the first thing we do when we wake up, and it's the last thing that we do before we go to bed. So any reference model from AWS will always have an extremely heavy security bend. And we've got a rich suite of services and products that make security easy to implement and integrate into your own environments. Secondly, networking, of course, that will provide the connectivity between all the architectural components that's required. There is also compute capability that's required within a reference architecture. This compute capability may be for processing, it may be for storage, it may be for transforming and augmenting data. Of course, we're talking about big data and IoT here, so we must have a data source. This data source could be as simple as a simple time-stamped temperature value, or it could be really complex health sciences and health life sciences data, things like real-time blood glucose monitoring data. So you have to be able to handle a wide array of data in a wide array of data formats. The beauty of this architecture is when we generalize, we can abstract out the type of data and we can generalize it into just a simple concept of data and ensure that our implementation is data agnostic in the way it deals with it. We must be able to ingest this data in a secure, stable, scalable environment. We must be able to process this data in one of two or even both, batch processing and real-time processing, and we're actually going to look at both of these in detail a little bit later in the presentation. We must be able to analyze this data. We must be able to turn data into meaningful insights. We don't give a definition to what those insights are. Meaningful means whatever is meaningful to you and your customers, but we must have an engine capable of turning data into information and even visualizing that information. And then we have to be able to store this so we can fetch this data back at any point in time in the future, and we can look back over time. So this is our generalized reference architecture. What happens when we start overlaying the AWS services into this architecture? Well, you get a generalized model that looks like this. Amazon VPC supplying the network capabilities in a secure cloud fashion. Amazon EC2 potentially, or even Lambda, being used as in the compute layer. AWS IoT is your data source. That data source can feed into the Kinesis suite of families, and we'll talk about how we do that in detail. Kinesis Firehose, Kinesis Streams provide the batch and the real-time processing, and Kinesis Analytics enables us to run real-time analytics over this streaming or batched data. And then our suite of RDS databases and Amazon S3 allow us to store this data so we can access it over time. And of course, security being job zero at AWS, we highly leverage our identity access and management and other security products in our portfolio to wrap all this to ensure this is a highly secure environment. What we're going to focus on in today's session is we're going to deep dive into those areas of the architecture that are highlighted in red. So we're going to go through Kinesis, and we're going to go through all three of the Kinesis family members, and we're going to go into how we store this data. So let's start to dig into IoT a little bit. And you've heard me use the term thing. And actually somebody even asked me this morning, so what is IoT? And what's this thing that you talk about, this IoT thing? There is no one single answer to that. An IoT thing could be something as simple as an iOS device. Could be something as simple as a Kindle or a Fire tablet. We're seeing a proliferation of IoT-enabled embedded devices in the maker community, like the Arduino, like the Raspberry Pi. For those of you who are familiar with the Intel Edison, that's also considered an IoT thing. Embedded devices and wearables are becoming incredibly popular. Most of us are now carrying heart rate monitors on our wrists that are watching our heart rate, sending data to be analyzed in the cloud. We're also seeing things being related to the proliferation of the smart home, the ability to instrument things like smoke alarms, temperature sensors, light globes, and switches in our homes. So we see a thing being anything that's connected to the internet from which we can acquire data, process that data, and present that data. There is a well-known IoT framework within AWS, and it consists primarily of the 7 elements you see on the board. I'm going to touch on each one of them, but we're going to go deeper into only one of them today. The AWS IoT Device Gateway, or Message Broker, provides a secure mechanism for these IoT things that we've just spoken about to publish and receive messages. We use the MQTT protocol to manage and to transport the publication and subscription to what we call topics upon which you'll receive and send data. We use HTTPS as a transport methodology. This is effectively the AWS IoT endpoint. It is also capable of doing WebSockets. And the real-time data that you saw in that demo that was coming in was actually coming from the IoT web broker through an authenticated connection using SIG-v4 signing down to a browser in real time over WebSockets. And that was raw MQTT data that had come all the way through the AWS platform being delivered to the end user. The next thing I'd like to talk about is the device shadow. The device shadow is a unique concept in AWS IoT, and it enables the persistent state of information to be held within the thing, even during times of intermittent network connectivity. So this is an extremely powerful capability that enables you to control AWS IoT service and the things attached to that service, even when the connectivity to that device is intermittent or that device is not even connected. When it does connect, optimistic locking will take care of ensuring that that device gets the latest version of the state, and the reported state and the desired states are synchronized. So when the device comes back online, it should always have its latest state. The rules engine in the AWS IoT service enables us to take these MQTT messages that are flying around our architecture and to transform these messages based on specific rules, and then to be able to route these messages to other AWS services or even to third-party services. And this is the one that we're going to do a little bit of a deep dive into. So the AWS IoT rules engine gives your device the ability to interact with other AWS services. Rules are analyzed, and then actions are performed based on the MQTT topic stream. And they can be routed to other services. For example, It could be used to augment or filter data received from a specific device or a thing. It could be used to write that data to a DynamoDB table. It could be used to save that data into Amazon S3. And it can even be used to republish that data to other MQTT topics that are not even in your AWS account. So this can be used to get MQTT and IoTT data, IoTT, that's a new one, IoT data between accounts. So it's extremely powerful, and it uses a SQL-like language, which means most of us can get in there and start having a play with it because it's a very, very familiar query language for us to use. Authentication and authorization, this is a security layer of the IoT service, and it provides security with mutual authentication and end-to-end encryption. I touched on before the SIG-v4 signing of requests. It integrates nicely with the Amazon Cognito service for user pools and federated identities as well, which means devices or things can have policies and profiles that only allow them to either send or receive on specific IoT topics, but also humans who are interfacing with browsers and logging into portals will also be able to get an IoT policy which allows the IoT service to either send or not send, or allow the user to interact with certain MQTT streams from their browser. That's where I'll end up. I've given you a high-level overview of the architecture, a generalized architecture and a specific architecture. Daniel's going to do a deep dive on the more complex areas. Thanks, Daniel.
All right, thanks, Mark. Alrighty, so what we're going to do now, we're going to take that reference architecture and apply it to the use case that Mark went through at the start of the presentation, so the global weather service architecture. So yesterday, for those who have just arrived, we ran a boot camp, and we had 100 attendees attend the boot camp where they were given an Intel Edison that represented a weather station. So we had weather stations that were allocated to cities around the United States. And each weather station had environmental sensor data that was getting aggregated to that weather station, processed, and then sent to the AWS IoT service. And we had the challenge of acquiring the sensor data from those weather stations at scale, processing and analyzing the data, and then presenting the data. And all of this using a serverless architecture framework. So having a look, it's broken up into 3 segments. So on the left-hand side there at the top, we have the acquisition phase. So we have the sensors, and the data is getting sent to the weather station and then sent into the AWS IoT service. So that's 1 sensor value per second per sensor. So we had 4 sensors, so 4 per second. And across all of the weather stations, that was 400 readings a second. And then the bridge between the acquisition and the processing section was the SNS topic. And I'll talk about why we use SNS there. We could have gone directly to the Lambda function or the Kinesis Firehose stream or the Kinesis stream. And then the data was processed and streamed into the data sources, both for batch and real time. And then from the demo that you saw earlier, the user interface, we use Cognito for the authentication and authorization to then access API gateway to then query historical weather data and the summarized weather data coming out of Kinesis Analytics. And then the real-time MQTT data was sent over WebSockets to that web application, so a single-page web application running JavaScript. All right, so what we're going to do today, we're going to focus on the acquisition and the processing section. We're not going to focus on the present side of things, but after the presentation today, we'd be more than happy to talk about that. So let's dive into the acquisition. So we had our 4 sensors: rain, wind, temperature, and vibration. Then we had the Intel Edison acting as the weather station, and that was aggregating the data, processing it, applying a Kelman filter, and then the data was being securely sent to the AWS IoT gateway. So there was a certificate, a unique certificate on each device, and then an IoT policy that was applied to that certificate on the IoT server side that allowed the weather station to publish messages to a specific MQT topic or a set of topics, and also subscribe. From there, we applied an IoT rule to the incoming sensor data, so using the SQL query to transform that data and augment it. And then using an IoT action, we sent it to an SNS topic. We also, which isn't displayed here, we also, because all the sensor data was coming on 4 separate topics, we actually also republished to a single topic. So we had all the sensor data streaming into a single topic for debugging. Okay, so now we're at the bridge. So let's take a look at the processing section and how that all fits together. So the IoT action combined with the SNS topic is the bridge. And we can see that there's a Lambda function subscribed to the SNS topic. And behind the scenes, we're leveraging multiple Lambda functions. So we're using Amazon SNS to fan the data out. So we could have different applications consuming that data and processing that data at different speeds. I'll get into that a little bit later. But first, let's take a look at how we're using the IoT rule and how it's set up. So our incoming MQTT topic structure looked like this. So we had a prefix, and in total 6 segments in the topic, where we had the state, where the station was in, the city, the station ID, the sensor type, and the sensor ID. So that was populated with the appropriate sensors data. Then the SQL statement looked like this. So we selected all the data from the incoming payload, and then what we did, we used some inbuilt functions so to extract the topic segments to then transform and put into the output payload. So we wanted the sensor ID, the station ID, the sensor type, and then from the incoming payload, the sensor timestamp, and then the various sensor values. And we used the cast function to make sure all the sensor values were in the same format. All right, so the incoming payload looked something like this. So that's the raw sensor data. And then by applying the SQL query, so the IoT rule, we can see at the top in bold is the topic segments. And then you can see the smooth, we just highlighted one there. We actually renamed that and also applied the cast function. All right, so let's focus in on SNS and why we used it for fan out. So we were using multiple Lambda functions in the bootcamp. So for our use case, we had the participants building out this architecture end-to-end in their own AWS account. So we had a Lambda function that was streaming the data and processing the data into Kinesis Firehose and a Kinesis stream. However, on the user interface, we could also see the global weather view, so a map of the United States. And in order to present that map, we needed to aggregate the data to a central AWS account. So we had another Lambda function that was assuming a cross-account role and then sending the data to a Kinesis stream and a Kinesis Firehose stream in the global weather service account. And you could imagine if we were doing this in a real-life scenario, a weather station wouldn't have an individual AWS account association. It would be many weather stations associated with a single AWS account, so using the IoT service in a single account. So the first function we named the IoT loader. So that loaded the data into the Firehose delivery stream and the Kinesis stream. And then we had another version of this called the cross-account IoT loader. So using the Identity and Access Management Service and the Secure Token Service API, it assumed a cross-account role from the Global Weather Service account. So there was a role and had policies defined that allowed the assuming party to put records into the Kinesis streams. Then we had another function called the RDS loader function. And what this function did was load the raw sensor data into the Aurora database and the summarized sensor data coming out of the Kinesis stream from the Kinesis Analytics application. And one thing to note, on the way in to the database, we're using this Lambda function to dedupe the data, because at scale, services like SNS and IoT can deliver a message more than once. So from our API, when we're querying the data in Aurora, we want to make sure, because we're doing aggregation and summing and counting functions, we want to make sure that the data is consistent. It's giving us an accurate representation of that data. Now, on the other hand, with Redshift, it doesn't matter if dupes are being delivered because it can process data at scale. We can easily create a view and look at those results for reporting and analytics. All right, so this is where we're using all the Kinesis services. So let's take a closer look at all the services and do a quick recap. So there's Kinesis Streams, and that's targeted towards technical developers. So you can build your own custom application that processes and analyzes streaming data. Then there's Firehose for ETL, targeted towards data engineers. So you can easily load massive amounts of streaming data into S3, Amazon Redshift, and Amazon Elasticsearch. And then Kinesis Analytics, targeted towards developers and data scientists to easily analyze data just by writing SQL queries. So let's look at key characteristics of the services. Kinesis Streams is for low latency streaming ingestion at scale. Kinesis Analytics for near real-time analytics of streaming data, so from a Firehose delivery stream or a Kinesis stream, and it'll deliver to an output stream. And then Firehose for batch data delivery. So you can base the batch data delivery either on time or size, and that goes into S3, Redshift, and Elasticsearch. Now, why would you pick Firehose over a Kinesis stream? Well, looking at a Kinesis stream, if you've got the requirement to process data using a custom application of the incoming records with sub-second latency, and using your own framework, then Kinesis Streams would probably be a good choice there. If you were looking at Kinesis Firehose and you were considering zero administration and the ability to use existing analytics tools based on S3, Redshift, or Elasticsearch, and you were happy with the latency of 60 seconds or greater to access the data, then Firehose is a good choice. And another thing to consider too, when ingesting data with Firehose, you don't need to worry about scaling the incoming rate for the ingestion on the service. It does it automatically. With Kinesis Streams, they're made up of shards, so you need to take a look at the amount of data coming in and provision the amount of shards that are required to handle that data rate on the incoming and the outgoing processing. And to make that easier, we've just released a new API that makes it easy to scale up your shards in a Kinesis stream. And there's a blog post on the Big Data and Analytics AWS blog that goes into detail on how to do this. So using a CloudWatch alarm to trigger a Lambda function that then calls this new API to easily scale up your Kinesis stream. Okay, so looking at Kinesis Analytics. So to set up a Kinesis Analytics application, we simply connect an incoming stream. So that can be a Firehose stream or a Kinesis stream. We write some SQL, and then it will constantly deliver results out to an output stream. And that can be a Kinesis stream or a Firehose stream. So this is where we're using the Kinesis Analytics application. You can see the input stream and the output stream, and then you can see the Lambda function processing the output stream. And one thing to note with Lambda, it supports different triggers. So here we're using the Kinesis trigger, which will batch load data out of the Kinesis stream, and you can define the batch size, and that'll constantly checkpoint where it's up to in processing the stream, and then you can process and deliver the results to wherever you need to deliver them to. So in this case, Aurora. So looking at Kinesis Analytics, what questions are we trying to answer? So if we go back to the user interface we saw in the demo, let's take a look at where the different data sources are coming from. So we've got the current value of a sensor, and that's coming over WebSockets from the IoT gateway. Then we have the average value. So that's the average value over a specific time period. So what we were doing, we wanted to know the average value over the last 60 seconds. So this was queried via the API. But you could easily use the IoT service and use pub sub to also get that value. So you don't have to constantly poll an API. Then for the minimum observed value and the maximum observed value, that was obtained via the API using a SQL query. And then the short-term graphing trending, that was acquired by MQTT data. And then on the other side, we can see that there's a historical view of the data, so the average, and that was obtained by querying the API, and that was from the data delivered out from our Kinesis Analytics application. And then finally, we wanted to get some statistics around our sensors, so the sensor uptime, the message rate per minute, so that was obtained from Kinesis Analytics, and also the total number of messages that had been delivered to date. So here's the Kinesis Analytics web console. And a SQL query, when you define one for Kinesis Analytics, is broken up into 3 parts. So the first part of the statement defines what the output payload looks like. And then we create a pump to stream the data to the destination stream. And then over the incoming stream, we select the data we want and then define the functions we want to apply. So we're averaging the sensor data, summing it up, so both for the smooth and non-smooth values, and then counting the number of messages that we saw in that minute. And it's over a window. So here we can see that we're using a tumbling window. There's also a sliding window, and where we have group by that defines a tumbling window. If it says window, then it's sliding. And so that's over a 60-second period. And you can see in the user interface here as well the real-time data being delivered based on the SQL query, so you can test the queries. Kinesis Analytics is a declarative system, so we just simply define the SQL and takes care of the rest of the processing and the delivery of the data. And it also will discover the schema of the incoming data the first time you start up the application. And the data can be in CSV format or JSON, and you can easily override the schema if you need to. All right, so when the data was coming in into the Kinesis Analytics application for each sensor, we were collecting it, and then at the end of the window, a single record would be emitted, and it looked like this. So it had the sensor ID, the sensor type, the station ID, and the average values, the sum values, and the message count. So you can see what the payload looked like, and then we loaded that directly into a database table. Okay, let's take a look at the data stores now. So we've got Redshift and Aurora. All right, so to recap, we're using Aurora for querying data via the API from the user interface. So that's the deduplicated raw sensor data and the summarized data. So imagine scaling from thousands to millions of API requests per minute. And depending on the throughput requirement driven by the Global Weather Service, at a certain point, Aurora would be more cost effective over other solutions like DynamoDB. And let's look at the specific use case here. At an API level, caching has very little benefit when you've got a whole lot of disparate queries occurring over a large time period. So if you've got disparate queries over a 10-year period, you may not have many cache hits. However, the last week or two might be queried more frequently. So that's where a layer and running a caching layer like Elasticache may have a benefit. So what Aurora allows us to do is scale out the reads really easily. It supports a reader endpoint, and we can simply add additional read replicas and use that reader endpoint in our application, not have to manage any complexity in our code in adding and removing the read replicas. So it makes it easy to scale out the reads. The other good thing with Aurora is that we don't have to worry about scaling the underlying storage because it uses S3, so we don't have to take any downtime to add more capacity there. And when we have our read replicas running and a primary, if it for whatever reason failed or we need to fail over, because it's got a consistent view of S3 because that's the underlying storage, there's zero data loss. All right, now let's take a look at Redshift. So we're using Redshift for our data warehouse, and there are many use cases. One use case could be correlating shopping trends against weather, data. That's one use case. And we could use Redshift to output some data and build a machine learning model. So for a general example, we could build a machine learning model. So we could have ATMs distributed around the country, and we could be getting real-time data from those ATMs via the IoT service, and we could query the Amazon machine learning service directly, and we could ask it, how likely is this ATM, how likely is it this ATM will fail? And it could return, a 1 or a 0 or on a scale. And based off that, we could then make a decision to send an engineer out to go and take a look at the ATM and repair it. And then that way we can minimize customer impact with an outage. All right, so in summary, let's take a look at the data store. So we've got S3, it's the basis for our data lake, the foundation, where we're storing long-term data, where it's warm, we can get to it quickly, it's secure, it's fully managed. There's lifecycle management, so we can lifecycle the objects to infrequently access S3, Glacier, or delete objects after we don't need them. Now, at times there might be questions when we first get the data and we don't know what to ask of that data, so we can easily reprocess that data using a supported framework that supports S3, and then use EMR to reprocess and load it back into Redshift for querying. Then we've got Redshift for an optimized data warehouse and analytics platform. So we can query large amounts of data really, really fast with Redshift, and we can easily scale by adding additional nodes there, so for storage or faster queries. And it's fully managed, so we don't have to manage any of the underlying infrastructure there. And then finally, Aurora, optimized for distributed data access, and we can easily scale the read throughput, and it's highly fault tolerant. All right, with that, I'm going to hand it over to Tim Bart from Hello to talk about their specific use case and how they're using AWS services to address their IoT analytics challenges around what they're doing with their sensors. So over to you, Tim.
Thanks, Daniel. Hi, guys, I'm Tim. And today I'm going to present to you what Hello does and the product that we've built over the last 2 years. As you can see, we're a company that does hardware, firmware, data science, and software. And since the product that you see there is an intelligent sleep tracking device. You can see Sense in its habitat on the bedstand and the little sleep pill that you clip to your pillow. The little pill on the pillow tracks your motion. The sensor on the table tracks the humidity, the temperature, the particulates, the air quality, the sound, the light in your bedroom. And we use all of that data to kind of understand how you sleep, when you sleep well and when you don't sleep well, and can recommend you to take actions when the conditions are not perfect. So today I will zoom in on our use of Amazon Kinesis for IoT data at Hello, which I think has been the most useful service from the AWS family that we're using. Before you read through those slides, I'd like to mention that when we started building this product, AWS IoT did not exist. And so we had to invent everything ourselves and roll everything ourselves. And so here you can see on this diagram that we have our ingestion ELB, which is the elastic load balancer, that receives all the data from our devices. We have a fleet of EC2 instances processing the data, verifying that the device is authorized and that the integrity of the data has been correct. And then we publish that data to a bunch of Kinesis streams. Those Kinesis streams are being processed by a few workers, and the workers store the data into different data stores. On the other hand, we have our mobile applications, which use a regular HTTP JSON API to query the data from different data stores like DynamoDB, Postgres, and so on. I'll zoom in on our use of Amazon Kinesis and what it means to use Kinesis for real-time processing and also like machine learning model building. So you can see on this diagram that we have a bunch of sensors, the humidity, particulates, light, sound. All of that data goes through one Kinesis stream. That stream is then being consumed by multiple workers. One of those workers whose role is to store the data in DynamoDB for easy access for online queries. So this is where we store the time series of all the data that each device has been processed. We have another worker whose role is to deserialize the binary data sent to our device and publishes to a Kinesis Firehose stream. The Firehose drops the data in S3 and also in Redshift, where we use Redshift as a source for data machine learning model building that we can use to then recommend better conditions for you to sleep. There are a few reasons why we chose to use Amazon Kinesis, and durability, immutability, and real-time processing were the key parts of why we decided to go with it. In terms of durability, it's very important for us to be able to offload the data as quickly as possible from our device. Our devices have kilobytes of RAM, and so we need to make sure that any data that has been collected need to be uploaded and processed and stored durably. And so what we do is we do a synchronous put record call to Amazon Kinesis on every data upload. It's synchronous on purpose. Once we receive a sequence number back from the Kinesis service, we know that the data has been processed, and now we can tell our devices to reclaim memory and space and continue processing data. We also send some other type of data, which is not sensor data, but diagnostic logs, which can be sent in batches. So the sensor data is being sent extremely often, so very small payload at a very, very high frequency. Then we have other much bigger payloads that are being sent at a slightly lower frequency. And so we can, by using a single platform like Amazon Kinesis, we can also process small and very frequent or larger and less frequent data payload. As you can potentially imagine through this process, it's possible for a device to attempt to upload the same data over and over again. And so what we've made sure to design is to have our databases be idempotent. So any message that is being published more than once is being stored only once in our databases. I will also recommend everybody to use a 7-day data retention for Kinesis. So if anything happens downstream, you have about 7 days to reprocess all of the data. One of the reasons why Kinesis is very different from other messaging systems is the notion of immutability. The message is published once, and you can have multiple consumers consuming the same message over and over again. As a rule of thumb, for every stream that we have about 10 consumers. Those consumers for us run on EC2 using the Amazon Kinesis library, and I will go into details about this in a few minutes. But you can also have consumers running on AWS Lambda, like Mark and Daniel presented today, and you can obviously mix and match both. In addition to having multiple consumers, you can have a consumer that processes multiple versions of your algorithm. So think of it if you had an alerting system and you're interested in trying a new way of aggregating data and alerting you that something is abnormal, then you can run version A, B, and C in parallel. And once you're confident that your new version is performing as well and as efficiently as you thought it would, all you have to do is stop the previous consumer. You do not have to change any code. You do not have to have a single application that processes and tries multiple algorithms. You can do that fully independently. One of the very interesting use case of Amazon Kinesis is the ability to process data in real time. And today I'd like to walk you through one of the use cases that you might face when you're starting to operate a fleet of tens of thousands or hundreds of thousands of devices. How do you know how many devices are online right now? How do you know how many devices uploaded data in the last 60 seconds? When was the last time that this very specific device was seen? And to answer all of those questions, at first, we decided to run SQL queries in our database. Simple select distinct count from sensor table and try to find what happened in the last 5 minutes. As you can imagine, with billions of data points, that query was not really scaling very well. And so we decided to build other consumers on top of the same Kinesis stream to answer those questions. One of the reasons why it's very easy to build those consumers is because Amazon provides the Kinesis client library, which is a library for Kinesis streams, which lets you implement a very simple interface that you can see here. And by implementing the 3 methods, you get access to a fully reliable, synchronized Kinesis consumer. And so today we'll spend some time looking at the process records method right in the middle, which is where most of your application logic lives. So to answer the question of when was the last time we saw each device, we've decided to implement this on top of Redis running on Elasticache. So what the consumer does is, for each record being provided by Amazon KCL, we parse the record. It's binary data, so we extract the fields that we want. We then store into a single key on Redis what the sensor ID was and what the timestamp of the data uploaded was. And by just inserting this data into Redis and be able to query that very efficiently, we do not have the need for this SQL query that was not scaling very well. And we can answer questions that were really difficult to answer before, like which devices hasn't uploaded data in the last 2 hours. This is pretty tricky to do in SQL efficiently. And so using a different storage for that solution on top of the other consumers are like processing the data to DynamoDB and to the Kinesis Firehose lets us answer this question multiple times a second and have a real-time view of the entire fleet. And once you have thousands of devices, knowing that everything is running smoothly is pretty good. And so maybe to conclude, I'll share with you a few lessons that we've learned. One thing I would highly recommend is to use the same stream for data archival and analysis. I am not suggesting using a single stream for everything, but doing the same analytics on the same stream guarantees that you have the same data source. There is no mismatch or application that forgot to be updated and where the data could be disparate. If you operate on the same stream, you have the same data. I will also advise you to sleep your streams early. The reason is, even if you don't need the capacity right now, you never know how many consumers you're going to have in the near future. And since each shard on Kinesis stream has a capacity limit, you want to make sure that adding a consumer is not impeding the entire scalability of your system. So if you can, I suggest splitting your shards very early. Use the Amazon Kinesis client library or the KCL if you can. If you're on the JVM, it's really trivial to write a consumer application, and Amazon takes care of shard synchronization, checkpointing, and really all you have to do is, given a list of records, store that data or process that data the way you want it. You can also run this on AWS Lambda if you wanted to, and I think one of the key points is you can mix and match. So if you need to prototype AWS Lambda, you won't be preventing another consumer from running that message. They all run in parallel and fully independently. And so the last point was like, yes, many independent consumers make writing those applications extremely trivial. They have one responsibility, they do it, and they don't need to know about other consumers. There is no synchronization required there. And the last few points are, especially dear to me, is choose your serialization protocol wisely. We operate on devices that have a very tiny CPU and very tiny amount of memory, and so we chose something that was really efficient for those devices, which is Google Protocol Buffer, and it worked very well for us. The only problem is like you need a custom deserializer to extract the binary data into something that other services can use, and this is one of the reasons why we're not yet using Amazon Kinesis Analytics, is because we need to transform the data from binary to a CSV format or a JSON format for it to be processed. And the last point is, I said earlier that for every stream we have about 10 consumers. You might run into some of the issues once you have too many consumers on the same stream. There is a limit to 5 reads per second per shard. And the solution to that is to use a fan-out strategy. Similar to what Daniel described today, I would strongly recommend using the AWS Lambda fan-out library, which lets you fan out one Kinesis stream into multiple AWS services, either other Kinesis stream or SQS and another system. And so with this, I'll end it to Mark.
Thanks, Tim. I think it was fantastic to have a look at a second use case that's actually used at scale and in production, serving multiple tens of thousands of customers. That was excellent. Thank you very much, Tim. We've covered a lot of ground today. We've covered a lot of technology. We've gone quite deep on some of them. But there are really 3 things that we want to leave you with as you continue your interesting reInvent journey over the week. The first one is that IoT with real-time analytics provides information, not just data. And it's the Kinesis Analytics component that we spoke about in the first architecture that enables you to take raw data and turn that into meaningful insights. Scale without intervention or cost. Using serverless architectures will enable you to take your designs and not put a cap on the number of customers, the number of services that you can deliver, and to do that without having to manually scale servers or platforms. And finally, we want to deliver architectures that remove management and scaling overhead and accelerate innovation. So the technologies that we've covered today enable you to focus on delivering true value to your customers rather than focusing on scaling up services and products. So with that, I'd like to say thank you very much for your time. It's been a pleasure spending some time with you this afternoon.